So we have our formula for carbon dating, and we just have to be careful that T is thousands of years. So if 2,000 years have gone by, T equals 2. I'm going to drop this into a spreadsheet. We want 2,000, 4,000, 6,000, and 8,000 years later. Oops, what did I do? There we go. All right, so here are the numbers I got. We've got about 78%, then about 62%, about 48%, and then about 38% after each of those. So hopefully your calculator is behaving well. Interesting thing about this table, 6,000 years after something has died, there's about half of the carbon-14 left, right? 48% rounds to about 50% in 6,000 years. So about 6,000 years is the half-life of carbon-14. So every 6,000 years, we should have about half of what we had before. So in 12,000 years total, we'd have about a quarter. Check that out, see if that's true. Yeah, so about half again, so that's almost 25% there. So it looks like the half-life is a little less than 6,000 years. And we talked about half-life of caffeine last week, if you remember. And this half-life idea will come up again in the homework. How much time do you need to get about half of what you started with? All right, questions on the first part, anyone? Okay. And hello, Tia, I didn't see you there, welcome. All right, so we've got our numbers plugged into that table. So the next question is about half-life, which I was just mentioning. And half-life, again, is the amount of time that has to go by so you get half of what you started with. And here it's stated the half-life is closer to 5,730 years, right? That's almost 6,000 years. And so one of these sentences best describes what half-life means for carbon-14. So your sentences will be in a different order than mine, probably. So take a look through them, and we'll have a vote in a minute about which is the best sentence. think I have my votes. And thinking about the writing principle for the class, if you write too little, you might not be saying enough. That doesn't mean the longest sentence is the best one. And in my calculator, I can debunk some of these. Will there ever be no carbon-14 left? That's a tricky question. If I look at my table, it keeps dropping. And 12,000 is a long time, but it's not quite zero. One of these said that it would be gone after 11,460. So if you take 5,730 and double it, you get 11,460. So I could plug that number into my spreadsheet, see what happens. 11,460, my spreadsheet says I get exactly a quarter, which is half of a half, right? I'm going to make a slightly different table here. What if instead of jumping by like 2,000, 4,000, 6,000, 8,000, what if I jumped by 5,680? 5,680. And then I just continued that. That's about 50%. Oh no, I didn't do that right. Was it 5,730? I did the wrong set of numbers. 5,730. There we go, half. And then I continue that pattern. So then I get half, a quarter, an eighth, a 16th, which would be half of an eighth. Half of a 16th would be a 32nd, is what's going on there. So again, this is half, and then this would be 1/4, 1/8, 1/16, 1/32. And that's like 30,000 years later, there's about 3% of the carbon-14 left. So it's not the first one. There will be none remaining after another 5,730 years. That's kind of the same as the first one. That's definitely false for me. Carbon-14 will start growing back. No, the stuff's dead and it's not growing anymore. So that one's out. So I think it's this one for me right here. The amount of carbon-14 remaining decreases by half in 5,730 years. Then after another 5,730 years, there will be half of that remaining. Yeah, that's what my spreadsheet told me when I made that calculation. I think that's the best answer there. Questions on that one, anyone? Moving along. The question number 3 here, notice there's the 5,730 in that second row. That's the half-life. So whenever 5,730 years go by, I should have half of what I started with. If I had 1 to start with, half of that would be 0.5. We just looked at in my spreadsheet 11,460 years later, and my spreadsheet said that was about a quarter, 0.25. So either on your spreadsheet or on your calculator, check 17,190, 22,920. See what those numbers are. Each of the numbers in the Y column here, if you check, they're 5,730 years apart as I move along here. So check on your calculator what we're going to get for the next 2 percentages. That's decimals. hopefully that worked out pretty good for you. I'm going to skip along here. We're next asked, an artifact is found and scientists determine that it contains 20% of its original carbon-14. So we want to use our numbers in the previous problem to estimate the age of the artifact. Okay, so 20%. Did we end up with any numbers that gave us about 20%? Well, 11,460 was 25%. For 17,190 years, I got 12.5%, so 0.125. Hopefully you got that number too. So 20% is somewhere in between 11,000 and 17,000. And so we want to make a guess at how many years that is. So 20% is closer to 25% than it is to 12.5%. So the answer is going to be closer to 11,000 than 17,000. I don't know. What do you think? 13,000 maybe? Somewhere in between these two right here. Let's see if the computer likes that. Hey, I did it right. Would it take 14,000 or is that too far? Hey, that one works too. Okay, so this is just a guess. Our guesses can be pretty wide ranging here. If you're not sure how I made that guess by looking at the table, let me know and I'll try to explain it again.
Could you explain it again?
Yes, I can. So I'm going to copy this into my spreadsheet to scribble on. Sorry, not my spreadsheet, my whiteboard. New page. All right. So I'm trying, come on, there we go. I'm trying to figure out when the carbon is gone, how many years have gone by so that the carbon is 20%. And 20% as a decimal is 0.2, which is somewhere in between 25% here and 12.5% there, which means the time that's gone by has to be somewhere between 11,000 and 17,000. So I was thinking 20% is closer to 25% than it is 12%, right? It's 5% away from here. It's like 7.5% away from there. So I thought the answer had to be closer to 11,000 years than 17,000 years. So my first guess was that, you know, maybe around 13,000 years. Now I can check that by plugging into my equation. If 13,000 years have gone by, that would be t equals 13, and I could see what does it end up being. Now they just said estimate, so that was a rough estimate. I could guess and check at the estimate by plugging into that equation 0.8861 and put 13 as the power and see if it's around 20%. So I'm going to do that just for fun. Somewhere I have a calculator about, I think on the screen, yeah. 0.8861 raised to 13, because that would be 13,000 years. And I get 21%, I'm close. So maybe it's closer to 14 years than 13. Hope that helped a little about how I made my guess.
Thank you.
You're welcome. All right. So we had to make some kind of guess by looking at this table up here, since 20% was in between these two rows right here. Okay, so moving on. Now we're actually asked to solve the equation here, and they're telling us that A is 20%. Okay, so an artifact is found, scientists determine it contains 20% of its original carbon-14. Determine the approximate age, that is T. And we want to state the answer as number of years to the nearest year. Okay, so let's try this together. So first thing I would write down on my paper is the equation, and the equation says A equals 0.8861 raised to the power T. They told me that A is 20%, which as a decimal is 0.2, 0.2. So that means I want to plug that in here. So now I have to solve 0.2 equals 0.8861 to the power of t. So based on our work last week, any thoughts on how I solve for a power? What do you got, Jesus?
Do you square root?
Not square root. That would be if it was the second power. If the power of the variable, what's another word? Sorry, if the power is an, I can't spit that out right. The exponent is a variable here. And what's another word that's synonymous with exponent?
Logarithm.
Logarithm, yeah, we got to use a logarithm here. Yeah, so the trick we learned last week is, there's my pen. Anytime you have a variable in the logarithm position, like that t right there, to move it out of the variable, you got to use logarithms. So what I do is I rewrite this whole thing as log of each side. So log of 0.2 equals log of that whole thing there, 0.8861 to the power t. So that's the first step in solving. So again, if the variable is an exponent, you have to use logs. The next thing that happens is, this is a special property of logs, that if you have the log of something to a power, the power pops out front. So now I can rewrite the left side as t times the log of that base. So we're applying lesson 4.3. This was the whole point of lesson 4.3 right here from last week. So again, first step is I take the log of each side. Second step is I bring the power down. Once the power is down, I can get rid of this multiplication by dividing by this log right here. And I have to do that on both sides. So on the left side, I have a number divided by itself, which is 1. 1 times t is t. I have solved for t. T is that fraction right there. The logs do not cancel. We tried to do that last week. It didn't go well for us. I just have to type that into my calculator. So then on my calculator, I'm just going to carefully type log of 0.2 divided by whatever division symbol your calculator uses. What's that Desmos calculator we were using before? We'll write it like that. My Google calculator uses this division. So let's see if we can agree on the answer here. So whip out your calculator, type that in. I'll try this in the Desmos calculator, make sure they agree. Oops. There we go. All right, so according to my Google calculator, 13.3-ish. T is in thousands of years, so that's 13,300 years. If I check with Desmos, which looks a little prettier, and I take, oh, and then I have to go to a different screen to get the log though. Pros and cons of all calculators. Use parentheses, please. And it looks like Desmos agrees with Google, 13.309-ish. So I got T is approximately 13.309. Let's see what was after that. 3. I went to 4 decimal places. All right, what does T mean again here? T stands for what? Years? Thousands of years? Something else? Thousands of years, right? So this is really 13,000. So to get the actual number of years, because again, this number is thousands, I have to rewrite it for the computer as 13309.3. They said to enter to the nearest year. So I think I would enter 13,309. Could I have screwed this up? Answer is yeah. So I think I'm going to double check by plugging that number in for t to see if it really works. And this is going to be a useful strategy on your upcoming exam that you know how to check, because there's no submit question button on the exam. So if I take 0.8861 and raise that to the power 13,003, oops, I missed a digit, 13,000, there we go, 309 years. Oh, wait a minute, that's not right, why not? T has to be the decimal version of that, 13.309. It says I get about 20%. Looks good. It's important to know how to check these. That submit question button is kind of a dangerous thing because it lets us keep doing it till we get it right. That doesn't happen on tests. We got to learn how to check ourselves. So important thing here is that to solve for an exponent like the t in the power here, I have to use logarithms to do so. All right, next page. And so this one is kind of interesting because what it does is it compares a regular scale where it looks like Mercury, Venus, Earth, and Mars are right next to each other compared to Jupiter, Saturn, Uranus, and Neptune. And then it looks at what's called the logarithmic scale, which just looks at the power. And notice the spread looks a lot different when we only look at the power of the distances. So for example, let's just double check one of these. Let's pick on Jupiter. All right, so I put Jupiter in my spreadsheet over here. See if I can find it, planets. So I'm trying to get my Zoom screen out of the way. So Jupiter is the one I'm going to focus on here. Let's highlight it. So Jupiter is 779 million kilometers away from, I think, the sun. Yes, from the sun. So I rewrote the number in millions of kilometers here. So the next thing I'm going to do is I'm going to ask, let's see, double check that I got that right. Yeah, I just want to know what power of 10 that is in millions of kilometers. So if I go to my spreadsheet again, and to get the power of 10 of a number like 779, you just take the log base 10 of it. So log 10, oops, spreadsheet, which is like the log button in Desmos of this number right here, is 2.89-ish. If I look at that new scale here, does Jupiter appear to be now at about 2.89? Well, this is 2.5, this is 3, and there are 1, 2, 3, 4, 5 spaces in between. So if this is 2.5 here, then this is 2.6, 2.7, 2.8, 2.9. Jupiter's right before that at 2.89. Okay, so again, what these positions are the power of 10 of each of the numbers from the table up here. That's how a logarithmic scale works. Use the log to find the power of 10. Notice they put Pluto right there. So here's what I need from you right now. What power of 10 is Pluto at? Right there. So if you could throw some numbers in the chat, let's see if we can find something to agree on. This is going to be important for the next question. What power of 10 do you think Pluto is at? Each of these are tenths. Okay, so we got a 3.78. Anyone else want to weigh in on that? Three 3.5, 3.6, 3.7, that's 3.8. I'm going to say 3.76. William says close enough to 3.8. Say 3.76. So we're just trying to estimate where that mark is on this number line. And this is a number line of powers, not actually distances. To get the actual distance, we raise 10 to that power. So whip out a calculator. I'm going to use my version. I'm going to say it's 10 raised to the power 3.76. Oops, I missed my power button and my decimal button. 3.76. So I get that Pluto must be about 5,754 million kilometers away. If we used a different power, oops, clear, 10 raised to the power 3.8, that gives us around 6,309 million kilometers away. So every time we change the power a little bit, we're going to get a slightly different answer. So like one of the other suggestions was 3.78. Oops, I missed my point. 6,025 million kilometers away. Okay, so it's, you know, it's in the high 5,000s or low 6,000 million kilometers away. So we have to make a decision about that. Round to the nearest million kilometer. So again, if I go with my version, which was 10 raised to the 3.76, the nearest, these numbers are in millions of kilometers, I would say it's about 5,754 million kilometers. Oops, did I get that right? What's it again? 5,754 was my guess. So you try your guess there, or go with mine. I don't know if I'm right. I haven't checked. I'm going to avoid that for a moment. It's killing me. I got to know. Am I right? Am I close? Ooh, I'm close. Okay. How about 6,000? Is that close enough? Oh, that's close enough too. Okay, so we got some wiggle room on that one. Hopefully yours went well. So we're going to reverse the idea right here. We're going to take an asteroid in the asteroid belt that's about 429 million kilometers. So that's that 429 there. We want to know what power of 10 is that? How do I find the power of 10? What's the trick? How do I find the power of 10?
Using log.
Yep, just use a log. So I would just take the log of 429 and that tells me the power of 10. And it's got to be the log, that's based on 10. So log of 429, I get it's the power 2.63-ish. So now I need to graph 2.63 on this number line, okay? And if you don't get the point in exactly the right spot, you can move it. Like suppose I put it there, that's the wrong spot. 2.5 is right here, 2.6 is next to it. I put it at more like 2.74 maybe. I can drag it to wherever I want it to be. So I'm guessing 2.63 is about there-ish. I think that's close enough. Yeah, so again, this number line is for powers of 10. So 2.5 is this mark, 3 is that mark. So like the scale above, it's scaled by tenths of the power. And again, this is called a logarithmic scale. Ooh, got it close enough. All right, we're kicking butt. And this is recorded in case you want to go back and view it later. Okay, so next problem. So data from the Dow Jones Industrial Average, which is a common measure of the overall worth of the entire stock market in the US, is graphed here from its start or early days of 1928 up through 2010. And, you know, money, there's inflation has happened since then. And so money is worth less than it used to be, or things cost more. You can think about it either way. So the numbers up here look really high, and you can't even see the changes down here because the new numbers are so much bigger. That line looks almost flat right there. If we zoomed in on that, we would find that's quite jagged in there. But we don't have a zoom on this because it's just a picture of a graph, not a real graph. It's regraphed below using a logarithmic scale. So notice here I have 2,000, 4,000, 6,000, 8,000 in the top graph. They're all equally spaced by 2,000. In the bottom graph, notice there's a big jump from 0 to 2,000, and then 4,000, 6,000, 8,000. They kind of get closer together there. So here we're graphing powers of 10. So the vertical scale is what's called a logarithmic scale. It's the same data, we're just plotting the power of 10 instead of the actual number. But that lets us zoom in on the early days, which is kind of nice. So we can get a better feel for what was happening in the early days. Now these two graphs are going to help us determine some information, but we're going to make some calculations first. So in this last paragraph of the intro here, we're given information about a drop that happened in 1929 and a drop that happened in 2008. And some of you might not remember this, but in 2008, there was a housing market crash that took down the whole stock exchange, and a whole bunch of banks failed in 2008. So it was a huge drop from 14,000 to 7,000 roughly. So what we want to do here is we want to calculate the absolute change for 1929. So what was the actual drop from 380 to 42? That's the absolute change. And we need to change that to a relative change. So I'm just going to remind you about how to do that. If you remember, feel free to move along. So absolute change is equal to the new amount minus the old amount. So for example, for 1928, they told me it dropped from 380 to 42. So 380 is the old amount, 42 is the new amount it dropped to. So that would be 42 minus 280. That's absolute change. Subtract the two numbers in the right order. Relative change is a percent change, as we call it sometimes also. Relative change is the absolute change. I can't spell absolute, that's better. Divided by the old amount, whatever that was. So we have to find this difference right here, and then take that difference and divide by the old amount, which was was it 280 or 380? Did I write that wrong? It is 380. I miswrote that. So what is 42 minus 380? I get a drop of 338. And then to get the relative change, we take that absolute change and divide by the old amount, which was the 380. And so I get around 88.9%. If I went to the nearest 1/10 of a percent, oops, wrong place. Which is a drop of about 88.9%. So that's a pretty big percent drop. The stocks dropped by almost 90%. It was catastrophic. Now, a note on the way the answers are asked for. We're looking for the size of the drop, so give your answers as positive values. Make sure you read the fine print. So for 1929, I would just say, hey, it dropped by 338, and the relative change to one decimal place. I missed that part. 338 is into one decimal place. As a percentage, yeah, that would be 88.9. That's all I got for that one. So I'm going to let you do the 2008 one, see what you get. Feel free to jump into the chat with any questions or answers to share. All right, what do we got in the chats? It looks like we have a drop of about 46.8%. And let's see, what did I get there? I would agree with that. And they said to go to the nearest 10th, so we would just go 46.8. So I think this one also, I agree, 46.8. And this absolute change was 6,600, right? So that's a pretty big absolute change, but based on what money was worth in 2008, it was only a 47% drop. Now I say only a 47% drop, that's huge, but it's not nearly as big as an almost 90% drop, okay? So in 2008, there was a bigger absolute change, but in 1929, that was a bigger relative change. So that means like if I had all my money invested in the Dow Jones, I just lost 90% of everything I had. Imagine that, right? If I was a millionaire, I now have 10% of a million, which is a lot for some people, but not for a millionaire, right? So they would have a hard time paying their bills on 10% of what they used to have. So there were lots of suicides in 1929 when the stock market crashed due to the amount of money people lost in a day. Now, let's think about this next part, and I'm going to copy these into my graph to try and estimate this for the next two questions. So I'm just going to highlight a couple of areas on my graph here. So 2008, that's this drop right here. And I can also see it again in this picture right here, 2008 drop. 1929 drop is right near the beginning here. And that's this drop right here we're looking at. Okay. This graph up here is showing us absolute change. And because we only have the powers down here, we're looking at relative changes over here. And so the next two questions are, well, which graph better shows the absolute change changes, which graph better shows the relative changes? And I think once you look at the pictures, you can pretty much see what's happening there. So in the top graph, this big jump here is that drop of 6,600, and I can hardly see the drop of 338 in 1928, 1929. However, in 1929, there was a 90% drop. And in 2008, it was only a 47% drop. So this is the 47% drop. This is the almost 90% drop over there. So the logarithmic scale allows me to better see the relative changes that are going on there, those percent changes. Any questions? And we are hopefully done with our lesson.